representing problem number 3, Lato Lato. If we attach a ball to each end of a string and then connect the center of the string to a pivot, when a pivot oscillates along the vertical direction, the balls will start to collide and oscillate with an increasing amplitude. We ought to investigate this phenomenon. First, it is important to know that the motion of the Lato Lato can be separated into parametric resonance and collision. This is an overview of my report. Let's start with my setup and equations of motion. We use a reciprocating machine with hamstrings of different names. The relevant parameters include the pivot's frequency, amplitude, the string's length and damping ratio for parametric resonance, the ball size and the coefficient of restitution for the collision between the two balls. So let's dive into our theory. Let's first talk about the gravity modulation by the fictitious force. Under the inertia frame, we can first assume that the motion of the pivot can be estimated as a simple harmonic. We can then, through second derivative, get the fictitious force, thus the effective gravitational acceleration. We can then consider the condition for string rigidity using the relative acceleration. We can separate this equation into 4 quadrants using the acceleration and the amplitude. We can denote that the only quadrant 1 and quadrant 3 satisfies our equation of motion. So we can then consider the finite size of the ball and get our equation of motion for the single pendulum, accounting for the gravity modulation and damping. We then consider the inelastic collision after a single pendulum motion, calculate the collision condition using the arc signs, then we set the initial conditions according to our coefficient of restitution. We then discretize the whole process using Euler's method. We then move on to characterize the damping ratio of different string lengths, and also the coefficient of restitution. Next, let's move on to my qualitative explanations. In my experimental data, we can see as the frequency ratio match reaches to 2, we can see a clear increase in the oscillation amplitude. While at exactly 2, the system damps out at the resonance breaks, demonstrating a frequency ratio match of the system. For the phenomenon explanation, we have observed at the pivot's highest point, the two balls will collide, and at the pivot's lowest point, a large angle will occur, demonstrating a phase difference in the phenomenon. Well, this is due to parametric excitation, where we can consider a gravity modulation. In the pivot's first half cycle, the gravity is larger than usual, and thus it couples with a large sine theta to maximize the work done into the system. While the opposite effect can be seen in the pivot's second half cycle, minimizing the loss. So both the positive work and the negative work will increase at resonance conditions. So we can plot the potential fields of the system. This is the original pendulum potential. Accounting for the gravity modulation, we can see that the trajectory of the Lato Lato ball aligns with the gradient of the potential. So the energy gained from the pivot's kinetic minus the energy loss dissipation will equate to the energy needed to overcome the field. At resonance, this increases. So we can write down the energy formula as this. And this, you can see a convergence of these and a dissipative of this. So a steady state may be possible. We can then move on to the amplitude fluctuations of the system. This is the data from our experimental video with the theory. We're taking the discrete Fourier transform, we can see multiple peaks forming. This is due to this motion being a complex harmonic. Zooming in to this cognitive beat, we can analyze the amplitude oscillations of the system. We then fitted a damp sign of 0.207 Hz, which is same as the difference between the driving frequency and the natural frequency, demonstrating that the ball is moving at these two multiple modes. We can then classify the two phases with the oscillating phase and the stable phase. Plotting the phase space diagram, we can see a limit cycle forming. This demonstrates the orbital stability of the system, where the amplitude increases with a plus and minus epsilon, as the epsilon will converge to the energy steady state that I have previously mentioned. We are also able to obtain a Foucault multiplier smaller than 1, indicating a stable orbit. We can then move on to investigate the stable state oscillations after we have done the experiment for a long time. plugging in the initial conditions, we can see a good quantitative agreement. Well, this is due to an asymmetric collision point oscillation, which we can actually see in our stable state frequency, where there is a new peak that is not a harmonic. This is because the center of mass of the pendulum ball will actually oscillate like a simple pendulum, thus giving us this new frequency. So now our equation accounts for the symmetry, asymmetry, gravity modulation, and the damping. We can then analyze the stable state frequency. We can see that the energy insertion roughly equals to the energy dissipation, with the inelastic collision being the main source of dissipation in this phenomenon. Next, let's move on to my dynamical driving frequency. At a driving frequency, there will be a resulting amplitude. This is called a jump resonance. When we increase the driving frequency, the resulting amplitude will decrease. If we then decrease the driving frequency, some previously not possible amplitudes become possible. This is because the energy is sufficient to maintain the system, but not sufficient to initiate it, demonstrating a hysteresis in the system. This is our experimental verification using a 25 centimeter string. The same effect can be seen with 45 and 35 centimeter strings. We can see that the resonating amplitude slightly increases from 2 times the natural frequency. Well, this is because the ball size deviated from the original parametric resonance. We can then investigate the effects of the string length. For small angles, the angular acceleration will be proportional to omega 0 squared. If we assume that at the stable state it is close to a sine function, this should be a cubic function. While for a simplifier explanation, at 25 centimeters, because the string length is very small, thus has less gravitational potential, so it can reach greater amplitudes. So lastly, we can plot a phase diagram with the O reaction, hysteresis, and the no reaction region with the string length and the driving frequency. We can then denote the increasing amplitude of what the proper statement had mentioned when we move from this region into this region. Well, this is an increase in the omega 0, making the initial conditions of initiation with a larger frequency. Next, let's move on to my further insights. With different driving frequencies, we give it a range of initial conditions. We then ran the simulation for a long time until a steady state was reached. We can see multiple steady states forming. This is due to the possibility of multiple oscillations per collision. Well, this is the hot bifurcations of the system, and this is the resonance. However, if we plot the experimental data, we can see that only k equals 1 is experimentally observed. This is because of the string condition that we have previously mentioned. Calculating the parameters, we can see that after a bigger frequency than 3.94 Hz, a stacking will occur, thus making the other steady states not possible in those strings. We can analyze the stacking movement on why it makes the increasing amplitude not possible. At a very high acceleration, the string will accelerate with multiple g's. Here, the string does not have enough time to accelerate. And at this negative acceleration, the ball will enter free fall, thus the ball will dance, making the increasing amplitude not possible in this situation. However, we have investigated the phenomenon with the fixed steady states. In our state, we can see that there are multiple oscillations per collision, which is our further insights. Next, we have investigated the phase 2 by our hands. We can denote the two phases by the phase 1, where we reach a stable state by slowly seeking the frequency, and the phase 2, where we suddenly increase the oscillation amplitude for a double collision. This is our experimental data from our hands. We can see that in phase 1, the amplitude are relatively consistent. In our phase 2, we suddenly pull down the system and make it reach. So we double collide, so the amplitude will no longer increase. We can then plot the phase transitions of the system under different amplitudes. This is the region where our EOM is invalid. And this is the region where we can move from phase 1 and after a sudden amplitude jump, go to phase 2. Well, the opposite direction is not possible due to hysteresis. So for the explanation, at quadrant 1, when the ball is reaching to 90 degrees, through a sudden pull, this amplitude will reach a negative value, thus making the string turn again. So it will safely reach to quadrant 3, getting a double collision. So this is a summary of the phases. At quadrant 1, only a single collision will occur. At quadrant 2, the string stacking will prevent the other possible steady states from happening. At quadrant 3, a double collision will occur when we suddenly increase the amplitude. And at quadrant 4, a phase failure will occur when the ball reaches larger than 90 degrees. So for the conclusion, we have classified the Lato Lato motion into 2 parts, including parametric resonance and inelastic collision. We have also explained qualitatively through coupling and the potential field on why the resonance will occur. We discretize the theory using Euler's method and find an excellent experimental agreement. We then explain the amplitude fluctuations and find the frequency of multiple modes. We also found a jump resonance in the system and verified the hysteresis experimentally. We plotted a phase diagram to explain how the string length affects the phenomenon. Lastly, in our further insight, we got the bifurcation diagram of the steady states of collision, and the phase 2 transitions was also discussed using the string's boundary conditions. Here is a total overview of my report, and thank you for listening.